Hello, in this video I'm going to show a cantilever beam under a distributed load, and it's some extra information to go along with this book. So here's what I'm going to discuss. I'm going to analyze a cantilever beam under a distributed load with help of hand calculations, and then check the results with help of SolidWorks Simulation. So here you see an example of a cantilever beam under a distributed load when a beam is completely incorporated inside a building on the left side and there's a weight standing on the right side. Then you could see this as a good example of a cantilever beam under a distributed load. Of course, you have to consider that this wall has got its own strength, so you could also argue that you should take a point load here in the middle. But if this wall is not that strong, for example the concrete is not that hardened yet, it would be an example, then this would be a very good way of analyzing this as a cantilever beam under a distributed load. So I'm going to analyze it later on with SolidWorks Simulation, and I'm going to use beam elements so that I will get a moment diagram, a shear moment diagram, and that's an advantage. Another advantage of beams elements is that it's fast. So here's what I'm going to analyze. I'm going to analyze a HE 100A profile under a distributed load of 100 Newton per millimeter. And then when you see the distributed load, you should also consider, is this a lot or not? And 1 meter times 100 Newton per millimeter means that it's in total 100,000 newtons, which is about 10,000 kilograms, and then that's the weight of about 10 cars. So that's a lot. So I'm not assuming this beam will be able to take this load. So whenever analyzing a beam, you should always create a virtual cut to be able to visualize the situation for yourself. And you can always erase a part of a beam and replace that part of a beam by the forces and moments that are playing inside this part of the beam. It makes everything pretty much clear. You can now immediately see that this moment has to be quite a lot larger than this moment over here, because this force over this distance is also adding a moment, so this one should be compensating for that as well. So then you know by doing this that the moment should increase from right to left in this beam. So here you see an image of why a moment leads to failure in a beam. Usually it's not the tensile or compressive forces. I've done that in chapter 14 of this book. I've done an integration of the moment that you have to have over here, and this integration, it says the yellow sticky note over here, you don't have to do that whenever using the moment of inertia, because then that integration is already done for you. The moment of inertia is analyzed by integrating the surface area, and SolidWorks Simulation and SolidWorks can help you with that as well, so I'll show that in the video later on. But this integration is only to make things clear for you, hopefully. Whenever using the moment of inertia, then this integration is already done for you, so I'll show that later on in this video as well. So now I can draw the shear and moment diagrams. The maximum shear force is the total force on the beam, which is 100,000 Newton, and it should be playing on the left, and on the right there's no inside shear force in the beam. And then since this moment diagram is the integrated version of this diagram, this one has to increase to the left as well, and then quadratically. So it's a function that is not linear but quadratic. So when I go to SolidWorks Simulation, I can also recreate this shear and moment diagrams and check them. So to do that, I'm using a template, simulation template, and the advantage of that is that it's already got the material set up inside, and now I only need to draw a line of 1 meter and then create beam elements with that. So here 1 meter, and then I'm gonna create a simulation study. First save the file, create a new simulation study. Exit the sketch, I was a bit too fast over here. I should first create the weldments. So create a structural member of this line, and the HE100 A profile is already pre-selected, as you can see over here. If you don't see it over here, this many profiles, you should download them with help of internet. Search on Google for download Weldman profile SolidWorks and you'll find how to do that. And now I'm ready to go to a new simulation study, and I'm gonna fix here the left side of the part, and now I'm gonna put the distributed load just similar to the one I showed in the presentation previously. So here under force, I'm gonna put a load distributed on the beam in a direction that I can select over here, this direction, and then it should be a force of 100 Newton per millimeter. By activating this checkbox, I can do that. So now it's 100 Newton per meter. I wanted 100 Newton per millimeter. I could change, of course, the units in SolidWorks, but I'm not going to do that. 100 Newton on a millimeter is the same as 100,000 Newton on a meter. Alright, so now I've got the simulation set up. I can save the file again and then run it. And now I see the stress, and the advantage of using beams is that I can define a beam diagram, and then I want to see the shear force. Let's have a look at that. You can plot quite some results, so let's first have a look at this. Here I see very small values. E minus 12 here says it's a very small value, so this is in the other direction, not the direction that I wanted to see. I wanted then to see the shear force in the second direction. This is better. And you can see it's increasing from right to left over here as well, and the maximum value is the same as I saw previously, so that's a good thing. And I can also define a beam diagram of the moment. So here. And now I can see that this maximum moment here is the same as I've just previously seen. So here, this graph increasing moment from right to left is the same as this graph with the same maximum value. So the moment graph is the integrated graph of this one. So you can already see that with 1 meter, the integrated graph, so the surface area under here is 100,000 times a half, and that's this value over here, because we have to integrate it over exactly 1 meter. So the maximum value here is the surface area under this graph, and that's half of the 100,000, so 50,000 Newton per Newton multiplied with meter. So this is the shear moment diagram, and now I can also calculate the maximum displacement. And if you look on internet for displacement in beams, you will find these easy to use formulas to analyze the displacement inside the beams for a lot of standard situations, like for example this cantilever beam under distributed load. So here I've already entered the values. I have to consistently always work with millimeters or with millimeters, but don't change within the calculation. So here I've chosen to work with millimeters, and then I can see when I enter all the values, the maximum displacement is 17.044 millimeters. So I can look at that in SolidWorks Simulation as well, and I can do something else here. I can change this graph to already here render the beam profile, so you can see that it's not just a round surface area but the real surface area that I used. And now I can see something else. I can change this to be floating numbers like that. I can see the displacement that I've calculated over here is quite a lot for a beam over a meter, but also I can see it's more than I've calculated over here. It's a difference of 1 millimeter, a little bit more than that, so it's too much. And the reason for that is that SolidWorks also takes into account the shear inside this beam, whereas your hand calculation doesn't do that. So what I can do now to be able to completely compare my calculation to the one that I've done by hand, I can edit the definition of this beam to have no shear factor. Actually, you shouldn't do that. Actually, your FEM analysis is more accurate than your hand analysis, because your hand analysis doesn't take the shear effect into account. And with short beams like this one of just 1 meter, that makes a considerable amount of difference. So I've changed that. I have to rerun the simulation, and now the result should be less accurate but more comparable to the one that I've calculated by hand. So 17.045, and it's exactly the same value as I have over here. Just over here I have one more decimal, but if I would increase the amount of decimals over here, it will be exactly the same. So let's do that. You see, so 100% accuracy over here now, and now I can go on to also compare the stress. So here I've done the calculation. Here I use the surface moment of inertia. You can see the value over here. You can calculate it by integrating, but also you can just request it from SolidWorks. I switched back to SolidWorks from simulation, and now I go to Tools, Evaluate, and then Section Properties, and I can see around the y-axis, the green arrow over here, I can see this surface moment of inertia, and this is exactly the same value as I have just entered. And in the other direction, so around the z-axis, it should be a smaller value, which I can see over here, which is a good thing. It shows I'm doing the right thing, because over this axis more material is on the outside, so this kind of beam is designed to take as much load as possible in this direction. So that's why you should always have this beam set up in this way. So I've checked the moment of inertia, the area moment of inertia. I've done that correctly in this calculation. So here I've got all the values set up correctly. The maximum stress should then be 687 Newton per square millimeter. So let's have a look. And then also here I can change this to show the beam profile like that. And then I can change these numbers to be floating. Okay. And then now I see exactly the same value, just one more decimal. So I could, for example, decrease the amount of decimals over here. But you see again 100% accuracy from your hand calculation compared to your SolidWorks simulation. So 687 Newton per square millimeter, which is too much, because in this case I've chosen a steel with a yield stress of 220 Newton per square millimeter. So it's failing quite badly as well in this case. So the expectation that I've written over here, that this weight is too much, is confirmed in this case. And then it's always good to present all of your results, and it's always nice to present your results when you have 100% accuracy. It's less nice when you have less accuracy. You have to give an explanation for that less accuracy. In this case, I don't have to do that. Everything is 100% accurate, so that's a good thing. And here it says that the factor of safety when using a material with a yield stress of 220 Newton per square millimeter is 0.32. So it can take this load. Roughly, it can only take a third of this load as a maximum. So that's what the factor of safety says. So that's what I wanted to show in this video of a cantilever beam under distributed load. So thanks for watching.